Hello my friends, today we're going to be talking about the derivative to get into what calculus is really about. So essentially the derivative is the collection of all the slopes of the original line put into a formula. That's what a derivative actually is. To generate the equation for the derivative, we can use this formula. This is a very important formula in chapter 2 and it's mandatory memorization. The idea is that we take f of a plus h minus f of a over h and we apply the limit as h approaches 0. This is why we spent all that time in chapter 2 going over limits, learning about how all this stuff works, simply to do this formula for derivatives. The symbol for derivative can vary a little bit. Sometimes they'll say f prime, this little quote in the air, of a. Sometimes they'll say y prime. Sometimes they'll say dy dx. If they say dy dx, what you generally want to do is solve for y equals, and then take the derivative with respect to x. Calculus is a lot about respect. If we're going to take the respect to x, all other letters in the problem we can treat as constants, which means they're much easier to work with. Technically, the derivative could also be thought of as an operation like a square root or a sine, and you can just apply d dx to f of x. Alright, so let's take a look at what this might be looking like. Here's a Sketchpad file, and the Sketchpad file is basically taking this cubic, this curve, and we've got the tangent line to it. This tangent line is running up and down. If you've got this tangent line, I'm going to animate the point, and I'm going to collect the slope of that tangent line. I'm going to record that slope as this moving red dot. So that red dot has the same x value as the tangent line, but the y value of the red dot is the slope of the tangent line. Probably the single most important thing you want to learn in the first half of calculus is that the y value of the derivative is the slope of the tangent line to the original. One more time. The y value of the derivative is the slope of the tangent line on the original, assuming they have the same x value. So if I just let this run, then all of these tangents will collect together in this red curve. So that red curve, that quadratic, is going to end up being the graph of the derivative of the original function. The power of calculus is that now I have a way to analyze the slope of this weird curvy original line via this quadratic. As we get better, I can get an equation for it, so now I can actually apply some math to it. Alright, so let's actually try and make this happen. The secret to making this happen is using our new formula. So our formula was the limit as h approaches 0 of f of x plus h minus f of x all over h. X or a, it really doesn't matter all that much, just so long as it's not an h. So what I want to do is, I want to keep my limit as h approaches 0. My f of is the square root, so I have the square root of x plus h minus the square root of x all over h. Basically, like any limit problem, I would try and plug a 0 into this and I would fail. It's not working. So my next bet is to try and use a little bit of creative algebra to try and jostle the problem around a little bit. Square roots have a trick that you can use on every square root problem, and that is to multiply by the conjugate. Remember, the conjugate is the exact same thing as the original problem, but the sign in the middle was minus. I'm now going to make it a plus. So I want to multiply that on top and bottom. Up top, when I FOIL that all together, it's going to make the square roots go away. I'm going to end up with an x plus h minus x. If you don't believe me, FOIL it out. I made the denominator more complicated, but that's okay because I got what I really wanted. This x and this x are going to cross each other out, and now I've got h over h. That h over h can just reduce to 1, and now I've got 1 over the square root of x plus h plus square root of x. This doesn't look like a big win, but now when I try and plug the h in for 0, I can actually get an answer. And I get 1 over square root of x plus square root of x. Or more simply, 1 over 2 root x. I guarantee you that if you're doing your algebra correctly, all the non-h's should cross out so that these h's can reduce. Guaranteed in every single one of these problems. If that does not happen, check your algebra. So that is A. Y prime is 1 over 2 root x. Slope of the tangent line to the graph of the equation at x equals 9. That's simply plugging in a 9 into the equation. I don't have to redo it all because I already have this generator. Instantaneous rate of change of y with respect to x at x equals 5. That's the exact same thing. So I'm just going to 1 over 2 root 5. And that's my answer. Oh no, technical difficulties. Alright, so this is going to be the same game. Slightly different setup, but same game. I start off with my limit as h approaches 0. F of x plus h minus f of x all over h. My new f of is x cubed. So I would do my limit as h approaches 0 of x plus h cubed minus x cubed all over h. And again, as is going to happen in every single problem, the h, if I try and plug 0 in for h, it doesn't work, so now I have to be creative algebra. For square roots, I use the conjugate. For powers, such as this 3, I just want to expand this x plus h. Probably would be a good idea to remind yourself of expanding a binomial, whether you want to use Pascal's triangle, or whether you want to use combinatorics, anything you want to use to be able to expand that. That should be something you should be able to do off the top of your head. If not, maybe check out Khan Academy and remind yourself of it. Once I expand that out, my x cubed and my x cubed are going to go away. Look at that. All my non-h's are gone, just like I promised. H approaches 0. Everybody loses an h if I just reduce. And now as h approaches 0, these back two terms are now 0, so they're gone, and my answer is 3x squared. So that's my derivative of x cubed. To sketch both of them, f of x is x cubed. It's going to look like that. And f prime is 3x squared. So it's going to look like that. So that's my f, that's my f prime. Fractions. Starting move is identical. We use our equation. So I'm just going to take all the x's in the problem, that's not very legible, and replace them with x plus h. So x plus h plus 1 minus x over x plus 1 all over h. Just like every other time, I try and plug 0 in for h and it doesn't work. So now I need to use some creative algebra. For square roots, I use the conjugate. For powers, I expand. For fractions, I want to multiply by the common denominator. So I want to multiply everybody by x plus h plus 1 times x plus 1. I want to multiply that to the top, and I want to multiply that to the bottom. When I multiply that through, this first piece is going to be x plus h. The x plus h plus 1s are going to cross out, times x plus 1. In this back piece, the x plus 1s are going to cross out. I'm going to be left with x times x plus h plus 1. On the bottom, I get a big mess. I get h times x plus h plus 1 times x plus 1. You're welcome to FOIL out the bottom if you really want, but pro tip, you don't really want to. It's just going to make for a lot more algebra that's not very helpful. What I do want to do is try and simplify that top, specifically to try and make the h's go away. So I get an x squared plus hx plus h minus x squared. Remember, this minus goes to everybody. Minus xh minus x. All over that same bottom. It's going to get annoying writing that bottom each time, but I ask you to do it. It's also going to get annoying to write this limit as h approaches 0 in front of each line of math. I would encourage you to keep doing that, just to remind yourself that it's there. X squared, negative x squared, hx, xh, same thing. X and x, look at that, all the non-h's went away. So I've got myself a limit as h approaches 0 of h over h is just going to be 1 over x plus h plus 1 times x plus 1. H becomes 0, so this is 1 over x plus 1 times x plus 1, or 1 over x plus 1 squared. This is my derivative. Find the slope at 3. That's just a matter of plugging 3 into that. So I get 1 over 4 squared. Find the equation at 3 is a little bit different. This 1/16 is my slope. and I find out x is 3, what I really need to be able to be done the tangent line is I need the y value in the original problem. So I take this 3 and I come back to the original problem and I plug it in. That's my tangent line. Be very careful whether or not they're asking for equation or whether they're asking for slope. Sketch the derivative. The key here is to remember all the fun things you know about derivatives. I know that the tangent line is going to be 0 at this first point. Oops, sorry. Because that's a flat tangent. I know we've got a flat tangent here, and I know we've got a flat tangent down here. So I know that my derivative is going to contain these 3 points. At this portion of the graph, I know that my tangent is negative. It's got a negative slope, which means the y value of my derivative should be negative. In between here, it's positive. In between here, it's negative, and then it finished off going positive. I don't know exactly how big the bumps are. That's really a relative move, and I would need a computer to know that for certain, but I have a rough idea of what it looks like. The screen is just barely too small. Okay, now this problem is really wacky because we're asked for dA d lambda, an altogether odd problem. But remember what you know about derivatives. The letter on top needs to be by itself, check. The letter on the bottom gets all my respect. So that lambda is the one that I'm going to actually do all my math on. So I do my limit as h approaches 0, and I would end up doing 3. I'm just going to switch to x's to make my life easier. X plus h squared minus x plus h, and then I would subtract 3x squared minus x. The first time I plugged in x plus h for all my lambdas, which is this whole first piece. The second time I just plugged in x for all my lambdas, and that's that piece. I would expand that out, try and cross everything out, try and make my h's go away to get my derivative. In my final answer, my dA d lambda should just have an equation as to what it looks like. So maybe like 6 lambda minus 1. That would be my final solution. Even if this produces 6x minus 1, I want to switch back to lambda. We're short on time, so I'm not actually going to show you that work. A problem like this one, where they ask me to find the derivative at 2 and the derivative at negative 3, it's probably a good idea to try and find the derivative at x, and then use that derivative equation to be able to generate your answer. So if I did my limit h approaches 0 of 2x plus h minus 3 minus quantity 2x minus 3 all over h. 2x and 2x are going to cross out, the 3 and 3 are going to cross out, and I'll be left with 2 times h over h, or just simply 2. At this moment, you might have realized the original graph was just a line. The original graph being a line means it has the same slope at all times. So the slope was 2, and I probably could have figured that out already without calculus. Tangents and normal lines. You've got your tangent line that's in red, the normal line is in blue. The normal line is perpendicular to the tangent line. Much like a tangent line, you do need a point on the original curve to be able to figure it out. The derivative will tell you the slope of the tangent line, and then you've got to go opposite reciprocal to figure out the slope of the normal line. Equation of the tangent at 2, equation of the normal line at 2. So first I got to figure out the slope of the tangent line. So do my whole limit thing. Short on time, so I don't think I'm actually going to be able to do this. And then plug in just the original in there. Expand it all out, get yourself an equation. Once you have your equation, plug 2 into that, and that will give you the slope of the tangent. Once you get that, go opposite reciprocal to get the normal. All right, so now you got a thumbnail view of derivatives. Enjoy.